In the draft tube, we see the water after working on the turbine imparts its energy to the vanes and runner, thereby reducing its pressure less than that of atmospheric pressure. As the water flow from higher pressure to lower pressure, it cannot come out of the turbine, and hence a divergent tube is connected to the end of the turbine. So draft tube is a divergent tube, one end of which is connected to the outlet of the turbine and other end is immersed well below the tail race water level. Major function of the draft tube is to increase the pressure from the inlet to outlet of the draft tube as it flows through it and hence increase it more than atmospheric pressure. The other function of is to safe discharge the water that has worked on the turbine or tail race. So you see, when you have experienced any real time force of water, when your tap broken, the water coming with some force, so that is the kind of force you can imagine. If if it's real time, is if it is flowing in the natural body, so it's running from some mountain or some heavy flow. If you're from heights, if the water has been falling from some on the surface or over the any exposed surface, so it will be experienced lot of force. So that force is was abundant. It was nobody can sustain that force. So all the things will be destroyed if it will be in front exposed to that force. So that force, to avoid any such damage to the those higher those such constructions of turbines, actually it is very costly, very lots of or requirement of economy is being used for power generation. So if it will be destroyed, so that will be for the safety of that we use this draft tube, so that it dissipates the energy safely which is coming to run the turbine. So it will just guide the system and dissipates the energy of water from higher to lower. Okay, so here are the some major parts of the draft tube. Let's see: generator drive, water inlet, runner, guide vanes, volute chamber. So this is the more enlarged pictures for that. This is showing you the direction of flow. Volute chamber, these are the guide vanes. Variable blades are there. The blades work as it will divide the energy of water. So now here you see this is the tube from where the flow is coming. Okay, this is the flow needle. Buckets are there. Water jet directors are there. Now these are the some dam you can see. So from this dam there is a system has been made. Okay, there is a structure you can see here. Some kinds of tube has been penstock has been provided, constructed. Here the water has been restrained by means of this dam. This is the head of the water, and this is the some valve is also there which is used to control the flow of water. By using this stop valve we can just close or open or release the water or can stop the water. So this is the few things for the dams. And then the penstock, water moves from here. Okay, all the blue section you can see there is a movement of water. And here is the turbine. This is a generator attached to it. Okay, now this one is the draft tube. This is a trail water where is water to be just given out. So here this is the real-time picture you can see. This has been attached and water has been dissipated safely out of the turbine. Okay. So what it do? Draft tube just safely dissipates the water energy so that no damage comes to the turbine or the any hydraulic system, hydraulic design of this section is been safely dissipate the energy of water coming to from the upstream to downstream. Now there are some types of draft tube you can see. First one is the surge tank. In the surge tank we see is a device introduced within a hydropower water conveyance systems having a rather long pressure conduct to absorb the excess pressure rise in case of sudden wall. So this is used, surge tank is used to maintain or to reduce the some pressure. So it is a device Introduced within the hydropower water conveyance systems, having a rather long pressure conduct to absorb the excess pressure rise in case of sudden valve. So it will just dissipate the energy coming from the reservoir, and the excess water will be, the pressure will be reduced. So valves closure, the surge tank is located between the almost horizontal or slightly inclined conduct and steeply sloping penstock and is designed as a chamber excavated in the mountain. It also acts as a small storage from which water may be supplied in case of sudden valve opening of the turbine. In case of sudden opening of turbine valve, there are chance of penstock collapse due to negative pressure generation if there is no surge tank. So you might have seen in your normal water tank over your over your roof or somewhere at the top of your terrace. So you see there is some kinds of opening at the top of those tanks. You find there is open pipe which is exposed to the atmosphere. That is a kind of balancing the pressure. So such type of arrangement you can see in the form of surge tank, which will, if there is excess pressure in the pipe, so there should be no damage to this penstock is been made. If there is high pressure, you see there is a head is very high, so water has been stored there beside the dams, reserve in the reservoir or the beside the dams. So you find there is lots of pressure coming from higher head to lower head, so there will be chance of damaging the this penstock or the valve or the other portion important portion of the turbines, which will causing the leakage or any such serious damage will be occurs in the turbine. So to avoid that, we use this surge tank, which will be, if the excess pressure will be inside this penstock, so that pressure will be just rise inside the surge tank and can spill or uh, can spill or can be reused when it is required. So these are some various functions for the surge tank. Next we have governing of turbines. How it works, let's see some pictures. By means of these pictures we'll try to understand. So governing means speed regulation. The speed regulation, this turbine should not be free to flow, that could be controlled in the control manner. So governing system or the governor is the main controller of the hydraulic turbine. The governor varies the water flow through the turbine to control its speeds or power output. So it is used to control the speed. So first one we have as the impulse turbine. In this we have three sections as the spare regulation, deflector regulation, and the combined one. So here you can see by means of some picture, this is the deflector actually. So here this is the penstock from where it is a kind of jet the water is allowed to pass through. Okay, now it is falling over the buckets, number of buckets of the various turbines you had seen. So now we have performance of turbines under unit quantities. As can see, the unit quantities gives the speed, discharge, and power for the particular turbine under a head of 1 meter, assuming the same efficiency. Unit quantities are used to predict the performance of turbine. So unit speed means, unit speed minus the speed of turbine working under unit head. So here you can see, so for unit power that will be denoted by PU, that is include unit power will include the power developed by the turbine and working under a unit head. Similarly, for the unit discharge, QU is we have the discharge of the turbine working under a unit head. These are the some major points. The specific speed can be calculated by using some equations as Nu is equals to N by under root H, and unit power Pu is given by P by under root H3. Now unit discharge Qu is given by Q by under root H. So specific speed of the turbine, that is given by Ns. The specific speed of the turbine is the speed at which the turbine will run when developing unit power under a unit head. So this is the type characteristic of the turbine. For a set of geometrically similar turbines, the specific speed will have the same value. So mathematically, there are some equations for the specific speed is given by ns is equals to n into under root p upon s to the power 5 5 by 4. These are the some equations we can use for this particular turbine. Further, we have there are some curves we get for the constant efficiency curves. So you can see at various heads or the variations, these kinds of curves you will get at different head and the pressure is generated 25%, 50%, 75 and 100. Similarly, this is the uniform, the constant. So this is the characteristic curve of the Pelton turbine. Similarly, we have more curves. This is a constant efficiency curve for the reaction turbine. The curves are plotted from data which can be obtained from the constant head and the constant speed curve. The object of obtaining this curve is to determine the zone of constant efficiency so that we can always run the turbines with maximum efficiency. This curve also gives a good idea about the performance of the turbine at various efficiencies. So, since we can experience the head variations due to the lack of water or excess of water in several seasons we have. In the rain time, there is plenty of water. In the dry season, we have lack of water. The the level of river you can see that decreases. So so depending upon that, we have some head. So we have to maintain the efficiency. So on that, we can just control by means of appropriate turbines and design. Then we have constant speed curves or operating curves, characteristic curve. In this, we can see various curves has been plotted that is showing you. So conducted at a constant speed vary the head and suitably adjusting the discharge. The power developed P is measured. So overall efficiency is aimed at the maximum value. So curve drawn between discharge efficiency and the pressure head you can see as P and naught and Q, that is discharge. Similarly, we can have number of curves on the basis of the discharge efficiency and the power of the turbines. So cavitation we had learned many times, that is to avoid any kind of air cavity formed inside the turbine or the workings of the blades. So if the pressure of the liquid is caused of its flow becomes equal to its vapor pressure at the existing temperature, then the liquid starts boiling and the pockets of the vapors are formed which create vapor locks to the flow and the flow is stopped. This phenomenon is known as cavitation. To avoid cavitation, the minimum pressure in the passage of the liquid flow should always be more than the vapor pressure of the liquid at the working temperature. In the reaction turbine, the point of minimum pressure is usually at the outlet end of the runner blades at the inlet of the draft tube. So cavitation we had learned already. It will to maintain the required pressure inside the system. We should not there should be the presence of liquid or water there. So methods, there are some methods. This is the important one. Some methods to avoid cavitation. Why it happens? So if the cavitation will be there, so the blades of the turbines will run freely because no vacuum will be created because it is running inside the cavitation. The vapor could be there, air space could be there, so it will not generate any suction and the system will not work. So that's why we should avoid this cavitation. There are some methods to avoid cavitation. First one says that runner turbine may be kept under water, so we should be keep the turbine underwater. The runners and all systems should be there filled with the water. Cavitation free runner may be designed, so you can just in the design part you can just design such a manner so there should be no empty space inside the runner. By selecting materials that can resist better the cavitation effect, by polishing the surface, by selecting a runner of proper specific speed for the given load, we can